Hello, everyone. I will first thank Antonio for arranging my talk in the last session. I was not available for other sessions. Um, I'm Mayusree from Indian Institute of Science. I work with Tomek Bulik and Banibroto Mukhopadhyay in continuous gravitational wave, wide dwarfs, neutron stars, etc. I'm finishing my PhD, fifth year PhD student right now. Okay, so I'll start my talk now. Thank you. Okay, so this will be about detection of continuous gravitational wave from accreting neutron star, accreting void dwarfs. First, I'll describe the objects which I'm going to talk about. So basically, these kind of void dwarfs are born from a common evolution scenario where there is a void dwarf which is accreting another main sequence star which has already surpassed the red giant stage. So this kind of object has a set of it. It's called Supersoft X-ray sources for a very good reason. So they emit in X-ray. They have been observed in our galaxy, maybe 3 to 4 of them. And people believe that there are more than 1,000 of these exist in our galaxy from stellar evolution simulation. So, and also people have observed them in emitting a luminosity around 10 to the power 4 solar luminosity. Now, I have mentioned 3 of the most popular, well-known supersoft X-ray sources. So I guess I have convinced you that why they are called supersoft because of the temperature. This is supersoft X. This is in the supersoft X-ray regime. Anyway, so these are the well-known sources. So point of our study. First, I should mention what is the motivation. Um, Basically, as I mentioned that because of the interstellar absorption, at least like, well, 1,000 of them are there, but we can only see 3 to 4 of them. So this is one of the thing that what if they are not visible to us? Can we still see them via some other means? So yes, the answer is, of course, we will talk about continuous gravitational wave. Then there is another very good motivation for this, is that these objects are known to be, supersoft X-ray sources are proposed or known to be the progenitor of type 1a supernovae. So when they accrete and they go beyond 1.4 solar mass, which is Chandrasekhar mass, so they burst to, I mean, they generate type 1a supernovae. To confirm this, we will have a gravitational wave emission from this system just before uh, just before the type 1a happens. So this is kind of a multi-messenger confirmation. Okay, so first I will talk about how do we model this white dwarf. For any kind of continuous gravitational wave emission from any compact object, I should mention that we have to model this kind of object in 2D. Because what we need is a time varying quadrupole moment from the system. And people believe that supersoft X-ray sources has some kind of magnetic field inside them, which is not very strong, but they have it. And they also have rotation, of course, because they're accreting. So what target here is that we are trying to say that even if this kind of white dwarf existed in isolation, they would still emit continuous gravitational wave. But anyway, so I will talk about the isolated system, how we model the continuous gravitational wave system, continuous gravitational wave from this kind of isolated system. So we can see that because of the internal magnetic field, this object can be deformed. If this has a misalignment, the system is accreting, so the chance of being misaligned is quite high. So then it can generate time varying non-zero quadrupole moment, which is the key of continuous gravitational wave or any kind of gravitational wave emission. So these are the well-known plus and cross polarization of this gravitational wave amplitude. What we want to study is this gravitational wave amplitude detectable or not? For that, we need to calculate the degree of deformation. How much is it distorted from spherical symmetry? Well, this picture is very exaggerated. The real picture, the real distortion will look like kind of like this. So this is a toroidal magnetic field. So this is the star is a little bit prolet in shape. And this is the polar magnetic field. because of that oblate. This is because of the anisotropic magnetic field pressure. So the model of this kind of object was done by solving Einstein's and Maxwell's equation together to generate this kind of field configuration and also the density contour. So why I'm talking about this is now from this picture, we will be able to get the moment of inertia along each of the axes, z and x. So now we can calculate the degree of deformation. For example, let's assume I was not talking about accreting system. Let's assume that I was talking about a magnetized white dwarf which is rotating. This is one of the famous white dwarf which has kind of high rotation, and we know the surface magnetic field. For this kind of object, for this object, we have like calculated, we have modeled this white dwarf with Einstein-Maxwell solver, and we have calculated the estimated gravitational wave amplitude. And we are trying to show that even isolated object you can see with LISA, upcoming LISA. Now I'm moving to the continuous gravitational wave. So for accreting system, we need to somehow connect this previous exploration of 2D static scenario where I can understand magnetic field and the shape of the star with stellar evolution, because now we are talking about accretion. So this is a MESA evolution code modified by us, where we have provided the magnetic field evolution. The magnetic field here is in 1D. So there is a 1D pressure, assuming that this is a toroidal field. From the previous picture you have seen that there is a magnetic field profile. We have provided this profile inside this MESA, and then we were evolving the magnetic field as well when the object is accreting. So basically what happens here is when the object accretes, the mass increases, the radius decreases, and kind of flux freezing happens. Yes. So what it means that the magnetic field increases, and the other decay time scale like ohmic and Hall decay time scales are quite high, quite large, so we forget about them, although they are really calculated inside this code. Anyway, so the most important thing here is the spin evolution, I will say, because gravitational amplitude also depends on the spin and the magnetic field amplitude. So I'll go to the spin evolution, and this is a cartoon picture. Don't take this very seriously. So let's say this was the white dwarf's magnetic sphere, and this is the accretion disk. Okay. So we would have to understand physical quantities in this system, which is first of all is the magnetospheric radius, inside which the accretion disk cannot exist because the matter rotates too fast in the magnetosphere. So it kind of ejects out the matter in the accretion disk, so accretion doesn't happen for that region. And accretion disk doesn't form that in that region. Accretion happens through polar magnetic field lines. So basically, and of course the other, this is very popular GECO-LAM model. So for other regime, of course, you will have spin up or spin down depending on this ratio Rm, which I was talking about, and Rc is at which radius the disk co-rotates with the star. Very simple, I think. So depending on these two conditions, the accretion might happen, might not happen. If the accretion happens, there might be spin ups, might be spin down. For example, just look at this curve. I was just showing the sign of the d omega dt, means spin up or spin down. For half of the time, there was spin up because of this term, because of accretion term. For half of this, there was spin down. But ultimately, there will be spin up only, because when the star is contracting, it's like a ballerina effect, and we will see a spin up. That term will win. So ultimately, we can see that the spin of the star is increasing, and well, the answer is probably very easy, that gravitational wave signal will also increase because the spin up is happening ultimately. Although there is a regime where the spin up really slowed down because of the accretion torque. So this is the evolution of the gravitational wave amplitude, and we can see that this is the last point before the type 1 supernova can happen. So this is kind of, this point we can measure with gravitational wave detectors, which can be a multi-messenger observation with the type 1 supernova, which can just happen after this. because no longer this system will generate any gravitational wave, which I was talking about. Now, this was a answer to the question, okay, was this a multi-messenger answer to type 1 supernovae or not? The answer was probably yes. Now, the second question, very briefly, because I have less time. In the galaxy, how many of these kind of objects we can search in blind search? So, of course, it's very easy to understand that when you have high gravitational amplitude from the source, you can go up to very large distance. For our kind of source, we found out that we can find out more than 10 of these sources in our galaxy, which is still more than the observed whole number of observed supersoft X sources in our galaxy. And how can we distinguish from the other object? There are other objects which will provide us similar kind of gravitational wave amplitude, but we can always think about the spin up or spin down rate. Does it resolve with the detector? If it does resolve, then we can understand the signs are different. See, for AMCVN system, they are coming closer, their spin will, and also double wide or similar. And for isolated, well, the spin decays. I have not talked about it, but there is a spin down. That is why the spin decays. And for this case also, spin up happens. But the frequency, we can think that in the end of the like simulation, what we have seen that the frequency is very high, like 0.02 hertz of the wide dwarf. I mean, before the type 1 happens. So we can clearly distinguish, because in this kind of frequency range, neither double wide dwarf resides nor NCVN resides. So for these two cases, I am comparing, remember, the in spiral period or frequency. And for this case, I was talking about spin frequency. So yes, that's all. Can we distinguish or not? Thank you.
Thank you. Do we have questions?
Yeah, interesting. And so if white dwarf is asymmetric, possibly no gravitational wave, so deformation is induced by magnetic field.
Yes.
So how much deformation needed to calculate your gravitational wave amplitude? What do you assume for?
So I have not write the plot here, but let's the deformation for these cases were like 10 to the power minus 4, which is quite high. I agree, but this is wide dwarf. For wide dwarf, deformation can go a little bit higher than the neutron source because its size is larger.
Okay, and first, why magnetic field is not really asymmetric? Why inducing asymmetry? Or?
Absolutely right. So in our assumption that magnetic field was asymmetric, and in this code we cannot simulate any asymmetric magnetic field. This is a stable solution. So our assumption was, let's take the misalignment after post-processing with this deformation, and the misalignment can be less than 3 degrees, which is kind of very well known that the system will not change that much.
Okay, yeah, thank you.
Another question? Yes.
Thanks a lot. I was wondering, do you have a feeling for how often could this scenario happen for carbon-oxygen white dwarfs leading to type 1As versus oxygen-neon white dwarfs leading to accretion
Yes. So I would answer this question a little bit hypothetically. So we know that the white dwarfs which are closer to 1.4 solar mass, and we are talking about right now 1.3 now, right? So they are oxygen-neon white dwarfs generally. It can definitely happen for carbon-oxygen white dwarfs also, which generally is less than 1 solar mass, right? The composition becomes more abundant towards higher, Z when the mass is higher. So I think that can definitely happen. We have also studied carbon-oxygen white dwarfs, which are 1 solar mass. And the result is kind of similar. It does not depend on.
I mean, do you think it's possible that some of those would not explode as type 1A, but collapse to form a magnetar?
Sure. What can happen is
maybe different transients.
Absolutely. Yeah. I think that can happen because, as you were mentioning, different transient. What can happen is, yes. So, for example, here, this Rm by Rc, whenever the ratio goes above 1, the accretion stops. And if accretion stops, you will not have type 1a. Right? Yes.
Thanks.
Thank you. I think we have to move on. We can thank the speaker again. And now our next speaker will be Jason Hinkle, which will speak about extreme nuclear transient.
There we go. Okay, perfect. Thanks very much. Very happy to be here today to tell you about some of the most extreme transients we've observed in the universe, why I think they're connected to tidal disruption events, and what that means about our ability to study some of the most massive quiescent black holes in the universe. So we've heard a little bit throughout this conference about TDs, but since I'm the first true TD talk, I wanted to spend just a little bit of time giving us a proper introduction. So as Wei mentioned, right, what happens in a TD is that an unlucky star gets a bit too close to a black hole, and as the star gets closer to the black hole, the differential tidal forces start to rip the star apart, or should at least stretch the star apart until it gets inside this tidal radius when the self-gravity of the star is overwhelmed by these tidal forces and the star is no longer bound. That material continues on its orbit, about half of it unbound and just leaves the system, whereas the other half stays bound and eventually falls back onto the black hole, some of it accreting and powering a luminous flare that we can observe across the electromagnetic spectrum. The fallback rate onto the black hole has been well understood for almost 40 years now, just basically following the orbits and the eventual accretion onto the black hole. And at least for a normal TD, so something like a low mass star, a million solar mass black hole, there's kind of two key things that I want you to take away. One is that the peak fallback rate, which we often assume is the accretion rate onto the black hole, although it might not actually be the same, is highly in excess of the Eddington ratio, right? So we're really in a regime of super Eddington accretion that almost no other accretion systems in the universe allow us to probe. And then as mentioned earlier, right, we have this kind of characteristic t to the minus 5/3 power law decline in the fallback, which we often see in the light curves, which is a little bit of a hallmark of these TDEs. Moving from just the fallback into what we might actually see in terms of their emission, there's been work done in the early days on what the SEDs might look like, basically taking this idea of Eddington limit accretion and a characteristic scale of the tidal radius. And when you put that together, you get something that peaks out somewhere in the soft X-ray to EUV. Although, of course, as you're probably well aware, most of the events that we see today are actually in the optical, but of course, we do see a bunch of X-ray selected events as well. And so in detail, right, this picture is quite a bit more complicated. But broadly speaking, the TDs that we have from optical surveys like Assassin, Atlas, and ZTF are broadly consistent with this picture, right? They have luminosities of order the Eddington ratio for the black holes on which they occur. They have temperatures that are hot and stay hot throughout the evolution. And then, very consistent with this picture of something that's powered by accretion, not just some exotic supernova or whatever. And so from that, TDs are very powerful probes of quiescent black holes, right? There's no requirement for anything else happening around the black hole, right? When you look at AGN samples and things like that, you need gas inflow to the central region, but all that needs to happen for a TD is two-body scattering, which just happens for free in the nuclear star clusters. And so if you add up the TDs as a function of black hole mass, which is shown here from very nice work from Yuhan Yao and the ZTF TD group, you can see some interesting things. First of all, most of the events we find as expected are around relatively low mass black holes, a few times 10 to the 5, 10 to the 6, the low end of the true supermass black hole mass function. And then there's also this precipitous drop at high black hole masses, somewhere around a few times 10 to the 5 or so. And what this is actually telling us is that at least at a population level, these are in fact TDEs. So this is the so-called Hills mass. And it's not that these stars aren't getting tidally disrupted. It's just that this tidal disruption happened inside the event horizon. And so there's no flare to observe. And so in principle, this is a hugely powerful tool, right? This is just the rate of TD as a function of black hole mass. But in principle, if you had a very strong theoretical expectation for what the rate as a function of black hole mass is, you could divide that and actually get a black hole mass function itself just from TDEs. Now, while I said this cutoff was a good thing and tells us that these are in fact TDEs, it also presents a problem, right? If we want to understand the most massive black holes, we simply can't use the kind of garden variety TDs that come from solar mass stars, M dwarfs, most of what we would expect from the IMF. But it's well known that there's this very nice scaling between the fallback rate of a TDE, or at least the fallback timescale, and the square root of the black hole mass. So in principle, if we wanted to go out searching for the most massive quiescent black holes, we should really just look for the very long timescale TDEs. But again, right, these are going to be rare, both because there's not that many massive black holes out there, but also, right, you're having to draw from more massive stars, or you have to get into some sort of odd spin configuration where you've matched a spinning black hole with a prograde stellar orbit for that TDE. But I think, as my talk title probably is given away, I think we've found some of these events. These are the so-called extreme nuclear transients. These are the events up in red here, extremely high luminosities, much more than the typical TDs, which sit maybe at 10 to the 44 or even down to 10 to the 43 at the lower luminosity end. But they're not only luminous, right? They're extremely long-lived, right? So this is consistent with this picture of a long fallback timescale coming from the fact that the orbits around the massive black holes are much longer, and therefore it takes a while for this material to actually eventually accrete onto the black hole. When you combine, of course, high luminosities and long timescales, you get that these events are incredibly energetic, right? Kind of standard supernovae TDs give of order 10 to the 51 ergs of energy. These are sitting somewhere in the neighborhood of 10 to the 53. So we're at 100 typical supernovae. We heard earlier, of course, about superluminous supernovae. Here we're still in a regime that's well in excess of what you might get from that, although I'll touch more on that later. We also know a little bit about their host galaxies. These are mostly at redshift 1 or so, and so it's a little bit hard to say. They're often detected in archival surveys, sometimes not. From typical host galaxy black hole scalings, we get black hole masses of about 10 to the 8, a few times 10 to the 8. And there's a range of AGN activity in these hosts. Some of them are strong AGN hosts. Some have no detections in pan-stars, for instance, and so it's very hard to fit an AGN in. And so it doesn't seem that there is a requirement for these to host an AGN to actually have these extreme transients. I just want to take a brief note, given that idea about AGNs, and perhaps, you might think if we're seeing a flare from an AGN, it's probably just an AGN flare. We do have a number of transients at low redshift that are consistent with this kind of mix of TDE-like observables, like a very thermal black body spectrum in the UV optical, but a more X-ray power law, kind of, this canonical X-ray corona in the AGN. But we're finding them at a pretty substantial rate. They're, broadly similar to TDE, so I think we can just take the relative rates and get a pretty good ballpark comparison of the true rates. And that's sitting somewhere in the neighborhood of 10% of the TD rate. And so if you just naively take the TD rate, you say that on average, about 10% of galaxies host some type of AGN disk. This is, I think, fully consistent. And there's a bunch of different literature that suggests that, plausibly, these are TDs and AGNs. So just to suggest that, when we go to these extreme nuclear transients and we look at them in comparison to TDs in blue, superluminous, supernovae in red, and the ants in this orange color, we see that the ants, at least in temperature, right, are fully consistent with this ant both temperature evolution, so they stay hot at something like 15,000 Kelvin throughout their evolution. They don't cool, right, so they're not supernovae. And then, of course, as I said, the luminosities are high, so for lower temperature, higher luminosity, or similar temperature, higher luminosity, you get a large radius. The same kind of picture is true when you look at the spectra. They're basically just these scaled up versions, right? You've turned up the luminosity, so naively that just comes from a higher mass star. But the spectra are fully consistent with some sort of accretion flare. They're very blue, they have the broad lines of hydrogen, sometimes helium. These are high enough redshift that we also see some magnesium too. There are some interesting behaviors, so some of them have these narrow lines that are somewhat reminiscent of circumstellar material. So that's a bit interesting, but as I'll get to in just a second, it's not possible to power the events from circumstellar interaction. It has to be accretion. And so we've seen various versions of this type of diagram many times in the conference. And of course, the ants are not the only things that are apparently very luminous, right? We have some types of beam transients that give us very high luminosities, but of course, it's not actually the true energies that we're seeing, and they're also much faster timescale. And so these ants are really sitting on their own, particularly even when we zoom into this kind of, canonical thermal transients that we study very often in the UV optical. They're sitting in this regime that's similarly long-lived to some long-lived supernovae and ambiguous nuclear transients, but the luminosities are far and away much more luminous. And again, right, this leads to incredible energies well in excess of any kind of standard optical transient that we've observed. And so this really does beg the question of what's powering them. I think I've already shared my viewpoint that these are TDs, but let me convince you why. So if you wanted them to be supernovae, there's basically just not enough energy to explain this budget. If you want it to be radioactive decay, you need basically the entire star to be made of nickel. If you want it to be CSM, for typical outflow velocity, you need hundreds of solar masses of CSM. Can't be a spinning neutron star because it would need to be too massive and maximally spinning. Maybe you say, okay, it's a normal supernovae, but you're getting help from lensing. The problem there is there's just no gravitational lenses to be found both in spectra or imaging, and you need a significant magnification. I said there was some evidence for AGNs in these hosts, but AGN activity, at least the normal stochastic AGN activity, doesn't work. It's too high amplitude and also very hard to get a coherent flare like the ones we've seen from just the stamped random walk like variability. There are some models of disk instability. So basically, if you can dump the inner portion of the disk on the free fall time, you do get broadly super Eddington accretion, these kind of long, perhaps coherent flares. The problem there is there's just not much predictions, and the parameter space is so wide that in principle you could explain anything. So it's hard to actually constrain that. And then of course, as I said, I think the high mass TDUs, so something in the neighborhood of 3 to 10 solar masses, fit very nicely, right? They explain the timescales, the energetics, and also if you do some crude rate estimates of basically taking the local rate of TDUs, scaling that to roughly redshift 1, and then accounting for both the fewer stars at the high mass end of the IMF and their shorter lifetimes, you get rates that are largely in the ballpark. And so I think these are high mass TDEs. And so, right, as I said, these are kind of our only probe of the very massive quiescent black holes in the universe. But even with that, where do we go from here? It's a very small sample. And so perhaps the obvious thing, which again has been brought up many times in this conference, is we want a bigger sample. So I think this is our biggest observational thing, is that with upcoming and just started surveys like Ultrasat, LSST, and Roman, we're going to have very increased depth that's going to allow us to potentially see these events out to cosmic noon. Roman in particular has excellent depth, although the concern there is that there's just not a large area with meaningful constraints. But in principle, these should allow us to build our sample over the years to come. But there's also, I think, some very important theoretical advances that we can make as a community. In particular, right, there's been a lot of work on trying to model normal TDEs, but these don't really work for masses of black holes that are 100 times in excess of a standard TDE mass, and stars that are very different. The structure of the star is very different. And so I think if we can extend our models to these types of extreme events, that's a promising way forward. And of course, I mentioned these disk instability models from AGNs. There's a huge parameter space here that we can actually, potentially get a flare from, but exactly where those would occur is not clear. And then, of course, what they would look like in either an SCD or a spectrum is also not clear. So it's very hard to compare, kind of these very broad MDOT things that aren't related to luminosity in a clear way to the flares that we see. But with that, I'm out of time, so I'm happy to leave you with my summary and take any questions that you have.
Thank you. Questions?
Hi, Jason. I have maybe a clarification question. So you said in the very early part of your talk, you talked about that these were super Eddington, but then you were like, oh, we don't actually really know if the accretion rate is connected to the fallback rate, but you connected the fallback rate to the super Eddington. So I was wondering if you could clarify that. But also, if this is super Eddington accretion, would we expect to see some form of outflow component here? Like you mentioned briefly some CSM stuff, but if we have any more concrete evidence for that?
Yeah, that's a great question. So I was a little bit unclear there. So it's clearly super Eddington fallback for lower mass black holes. So you basically, if you have the star of the given mass, right, that's your mass. And if the time scale gets stretched out as you go to higher mass black holes, the Eddington ratio drops, but it's still of order Eddington or mildly super Eddington. Right, I think the details on, so the fallback timescale still sets the overall timescale of the light curve, right, because that's what's feeding the black hole fundamentally. But I think what I was mentioning is the detail is it's not clear that what's falling back from where the disruption happens to what actually gets to the ISCO and accretes is always the same number.
Okay.
Right? There's a lot of details in anything accretion related to actually go from any sort of mass fallback or accretion rate into the luminosity. And that's what I was trying to say, is that it's a complicated picture. You can't just take the fallback that I showed and say that's what the light curve would look like.
Okay. And regarding the
outflow. So
the outflow part. Sorry.
we naively do expect that TDEs should power, outflows when they're in the super Eddington phase, right? Most TDEs are found to emit radio at some point in their evolution. These are very high redshift, and we don't actually have many constraints on the radio. But I think that, I know you didn't explicitly ask, but I do think radio is potentially a way forward to understand how this fits into that picture.
One last question, maybe.
I didn't follow your comparison between the spectra. Could you explain it again? I remember most luminous TDE, they are featureless. Are those ENTs are featureless or has hydrogen or helium lines?
So these do have lines of hydrogen and magnesium. This one has some narrow lines. So you're right that there is a class of claimed featureless TDEs. I think here, right, the picture is probably that it's really just the ionization state in the material, and there the temperatures and luminosities are, and you have a compact region, so things are highly ionized and you don't have the lines. But here the temperatures are lower, and so you still, it's fine that the luminosities are high, but you still see the lines, right, because it's not as compact.
Thank you. I'm sorry, we have to move on. Let's thanks again the speaker. And our next speaker will be Alberto Floris, and he will speak about polarization in TDE.
Thank you. So I'm Alberto Floris. I'm a PhD student at the University of Crete and the Institute of Astrophysics in Heraklion. And what I'm doing during my PhD is study the polarization properties of TDEs. So we just heard and we already saw this plot here, but tidal absorption events are indeed astrophysical transients that occur when a star gets disrupted by the supermassive black hole at the center of a galaxy when it ventures too close to it. And the initial idea was that TDEs, as it was detailed by Martin Rees, would mostly emit in the X-rays because the part of the material that stayed close to the supermassive black hole would eventually circularize, form an accretion disk that would start emitting X-rays, and we would be able to see it. And the initial model actually had quite some success because people started seeing transients that really looked like what was initially predicted. But eventually, when the optical transient factories and also in the UV started observing these transients from the center of galaxies, they started finding that the vast majority of TDEs were actually not exhibiting any X-ray emission, but most of them were really peaking in the UV and the optical. So what we had to do was to try to reinvent our models to try to explain this discrepancy in the population. So that's what I'm working on because we all tried to solve this discrepancy by making some models that would try to explain the observations and try to explain the presence of the optical and the UV. But, well, the people tried to create two main branches of these models. They are called the shock and reprocessing models. And, well, the basic idea for the reprocessing model is that we have the initial idea of the formation of an accretion disk that emits X-ray photons. But on top of that, we put an optically thick reprocessing layer that absorbs these X-rays, that doesn't allow us to see them, and then re-emits these photons at longer wavelengths. So we can observe the optical and the UV. This is the basic idea of the reprocessing model, while the shock model predicts that the vast majority of the emission in the optical and the UV would be coming from shocks from colliding stellar streams after the disruption of the star. So you understand that after some time, you have some loss of angular momentum that leads to the formation of the accretion disk. We are able eventually to probably see the X-rays if they are emitted, but clearly this is a more complex model. It predicts more multiple emitting regions. So it took a bit more time to really figure this out. But the issue here is that while these two families of models really appear very different, they basically predict the same observables. And this is a big issue when you want to really try to understand what is the real source of the emission from TDEs. And one way that we can try to constrain this is by observing them with polarization. And indeed, the reprocessing model basically predicts that we have a polarization degree that is low, below 6%, while we would have overall constant polarization, both in angle and degree, over the whole duration of the flare, while you see that the shock model is more chaotic, more dynamical, so it predicts basically more variability in polarization, and at the same time, no clear hard cap on the polarization degree, so we are not really sure what might be the maximum polarization, but overall, maybe high polarization. So this is what we do. We created the campaign of observations of tidal disruption events. It's called BOTES, with which we aim to track changes in polarization so that we can better understand if what our observations fit one model or the other. And we do this with these telescopes that you can see here. The main one that we use is the Skinacas 1.3 meter telescope, that one there, that is in Crete, where I am and where I go often to observe. But also I wanted to mention very quickly that very soon we will have facilities that will be able to even observe serendipitously a lot of TDEs in polarization. One of these, the first one that will be mounted is the VST pole polarimeter on the VLT survey telescope in Cerro Paranal in Chile. And this one will have a 1 square degree field of view, which will be able to give us measurements before, during, and potentially after the transients serendipitously. So this will be really invaluable for our type of research. And here I wanted to say that, well, initially we have been tricked into this kind of business by this very special event, 80-2020 MOT, that was a TDE that occurred in 2020 that exhibited a very unexpected degree of polarization, about 25%, together with very high, very variable polarization angle and degree. And this was particularly interesting because while people were mainly aiming at studying in polarization TDEs that were jetted, so that were exhibiting jets, of course, because people in polarization are usually interested in jets, well, we got tricked into this because this exhibited 25% polarization degree, and that's very far away from the 6% that is predicted from a reprocessing model. So indeed, this was putting the shock model back on the table. So what we did was we conducted a population study of these TDEs to really try to understand if 80-2020 MOT had anything special with it, or if we were simply missing something with the other TDEs. Starting from polarization, you can see that that's typically what we do in polarization. We study the evolution of the Q and U Stokes parameters that are the basic observed parameters in polarization. And just for reference, we put the 6% polarization degree circle that limits that is the limit for the reprocessing model. And you see that the vast majority of the measurements that we got were inside that circle, so overall consistent with the reprocessing model, while the 80-20-20 MOT was completely outside of this circle during the whole duration of the flare. And however, while this might tell us that 80-20-20 MOT was special, when we looked at the global parameters of this TDE, it was not special at all. It was very typical TDE, optical TDE, apart from its inferred polarization. So what this might be telling us is that we might simply be missing some high polarization states in other TDEs simply because we're not sampling their light curves in polarization densely enough. But we talked about the polarization degree. What about the polarization angle? It's the other parameter that we study in polarization. And as you see from this plot, when we studied it for all the objects in our sample, well, we find a whole zoo of behaviors in polarization angle that weren't initially expected. For example, we see some chaotic variability, some objects that have initial variability and then settle at a specific level of the polarization angle. And something that was even more unexpected, like this object 802024 PVU, that underwent so-called rotation, something that is observed only in blazars up to now, or jetted systems, let's say. But the intriguing thing is that 802024 PVU does not have any X-ray emission, no radio emission, nothing apart from this behavior that would tell us that this one has a jet. So what does this tell us? Overall, it tells us that TDEs are probably something more dynamical and more chaotic than we initially predicted, and this indeed is probably pointing to something that is shocks, or not, but not necessarily something that is constant and thus associated with a simple axisymmetric reprocessing model. And in the last few minutes that I have, I wanted to talk to you about this TDE, 802024 TVD. That's the last thing that I've been working on lately. And it's already been mentioned during this conference, but I will just say it again, that it is, and you can see it from this Hubble image, the first optically confirmed off-nuclear TDE that we found. And this was a very typical TDE at the start. It had a very typical optical light curve and a very typical optical TDE spectrum. But at the same time, this TDE eventually was discovered to be off-nuclear later. And also, it's eventually when the optical started decaying, the X-rays started rising. And we were very intrigued by this, and indeed also the TDE also showed some radio evolution with two different distinct flares, and we basically got some observations both at the optical peak and at the peak of the X-ray emission. And what we found was that since we wanted to really try to model this correctly, we subtracted the polarimetric image with a model of the host galaxy, and after we subtract it, we get that we have only the TDE, and once we measure the polarization, we get that it has a very high polarization, about 25%, consistent with the other TDE that I mentioned before. But in this case, we find that it has both X-ray emission and radio emission at the same time of the polarization measurement. So this potentially tells us that this might be a jet together with the high polarization. And so in this case, this would be the highest polarized jetted TDE to date. So that was an interesting result. And I will leave you with my conclusions, the fact that polarimetric measurements can indeed help us solve what powers TDEs and even find jets that we didn't know were there. And TDEs are likely intrinsically polarized, and we might be missing some highly polarized states in other TDEs, as we saw for 802020 MOT. And the TDE polarization appears variable both in angle and degree, and this is not consistent with a simple axisymmetric reprocessing model. So thank you, and I will take your questions.
Thank you. Questions? Yes.
Yeah, thanks for the nice talk. I'm curious for 24 TVD, with the X-rays, that probably tells you that you have a disk, and so that kind of disfavors at least the idea that the disk formation has to be slow, and so kind of naively you might expect that UV optical is reprocessing powered. So how do you kind of reconcile those two things?
Well, I have not. There are papers on this, and the main result that has been found is that at that time, at the peak of X-ray emission, the X-ray spectrum cannot simply be represented by an accretion disk, like a black body. You need also a power law component to really get a good fit. So, to me, that seems convincing enough to say that there is a non-thermal component there, together with the black body that might be the accretion disk that would launch the jet, maybe.
But I guess just to quickly follow, how do you connect that to the shock model? Because those don't seem connected.
No. This in the case of 802024 TVD, this would be a jet. The polarization would be coming from a jet. So in
In
the
the
other
optical?
cases, that's what
But
I'm
the
guessing.
optical is still thermal, right?
What?
The optical emission is still thermal, though.
Well, we have been looking into this, and there is a high chance that no, the optical emission is the polarization, as the polarization in the optical, and that is 25%. So you cannot explain that with a simple accretion disk. You need something else, and that would be, to me, a jet. So part of the optical emission is the jet.
Questions? Like this one.
Thank you. So a comment and a question. So I don't think so. We showed like in some papers like that in the reprocessing model you can get higher than 6%. So you can go up to 15 or even more percent. And also I don't think this change in polarization angle cannot be explained. This is actually something that, I mean, or even in supernova studies, you do see this flip in the Stokes Q, or I mean that you can get this 90 degree rotation. I mean, when you were showing that plot, I mean, some of those events seem to have this roughly 90 degree flip. I mean, change in the angle. So I don't think like the reprocessing model should be, I mean, would be ruled out by these high values. I mean, maybe 25 is a bit high, but also I wouldn't think you can rule it out by sorry, the polarization angle, especially if you are close to like this 90 degree rotation. And
no, that's true. Yeah. That's one of some of the cases. I'm not showing all of them here because we also studied Bowen fluorescence flares, but for simplicity, I showed the pure TDEs, and especially in the Bowen fluorescence flares, we see a lot of these 90 degree flips. So that is something that would be
these are like kind of optical depth effects, like in processing, like you can have some axis that is dominant at some time, but then it densities reduces, and then you get some.
Absolutely, I agree with you 100%. It's discussed in the paper, but of course, for simplicity reasons,
So my curiosity question is like, are you? So what I find hard of your papers is to understand this other shock model, whether it can get those values and can reproduce the observation, because you don't have models. Are you working on some models? Or
no, I'm not. I'm not a theorist, so I'm not selling any models specifically. But there are people that now finally are working on those models, because of course it's true that up to now we are working on an exclusion principle. So we see something that fits the constant polarization, we say, oh, this is reprocessing. We see something that doesn't, we say, this is shocks. But we don't really have real proof because we don't have the models that predict an exact number of polarization at specific lines of sight, for example. So indeed, that is coming. It's not from me, but you will see it.
Okay.
Okay, so this is the last talk you have to listen to this week about science. Thank you very much to the organizers for for allowing me to talk at this wonderful conference. I think we've all had a lot of fun. I'm going to end out the TDE session by talking about TDE 2025 ABCR. And we've been hearing a lot about how TDEs are cool. One thing we haven't really heard about at all is how we actually find TDEs in the first place, because obviously studying TDEs is downstream of discovering them. And so obviously we've heard what TDEs really are, but I would say that nowadays in the optical, we have what you could really call an empirical definition of a TDE. So a tidal disruption event is, to first order, a nuclear flare, which is intrinsically hot with blue emission. So this is an example of a light curve, and you've got obviously the optical and the UV, and it's very, very bright in the UV. TDEs rise over a period of, let's say, weeks, and then they fade over a period of months. And the other thing that you see immediately is that the gaps between all of these bands are roughly constant over time because TDEs do not cool. And this really distinguishes them from other transients because they have this roughly constant temperature. So if you would like to find tidal disruption events and you go and look in the centers of galaxies, unfortunately, you're not going to find just one thing, but several things. So of course, the TDEs, the things we're interested in, these are relatively slow transients on average. They are hot without cooling, and they are usually in the center of a galaxy. On the other hand, we have an abundance of supernovae. These are mostly fast transients, but not always. These can be hot as well, but they generally cool. And then supernovae are preferentially distributed away from the center of a galaxy. And then, of course, we also have active galactic nuclei. We know that these are variable sources, and they have a very characteristic SED, for example, in the radio or the mid-infrared, and AGN in general also live in the center of galaxies. And the whole game of discovering TDEs is basically trying to distinguish between these multiple classes. So how do we actually do it? I'm going to talk about my machine learning algorithm called TDE score. So TDE score is extremely simple. Basically what you do is if you take all of the light curves that you receive from ZTF, which we've been hearing a lot about at this conference, you get something that looks like this. This is sort of 30 different TDEs. What we do is we fit the underlying light curve shape with the Gaussian process. So you've already simplified from many data points to one shape. And then you make it even more simple than that. So with this Gaussian process, you just extract physically meaningful parameters. So how many days does it take to rise to peak? How many days does it take to fade from peak? What is the temperature at the peak? And how does the temperature change over time? And then what you can do is combine that with information about the host galaxies. So for example, what are the Y's W1 minus W2 colors? Is there a known radio source in the galaxy? And you can also consider properties about the detection itself. So when a source is detected, you see, for example, in ZTF, where the position of the transient is relative to the archival center of the galaxy, and you have the offset. And so what you do is you combine all of these into a very simple binary classifier that basically just provides scores. And if you're interested, read the paper. I'm not going to talk any more about how TDE score works in detail. Maybe just what I want to tell you is that TDE score is discovering lots of TDEs. So we started operating in real time 2 years ago now, and more than half of all new TDEs are discovered by TDE score, and most of the others are discovered by other machine learning algorithms. So we're now averaging something like 30 TDEs with ZTF every year, which is twice as much as we were doing before, but obviously pales in comparison to the absolute deluge we expect with Rubin very soon. So it's great that machine learning can automate our processes, and we've discovered a way to systematically discover TDEs, but we don't want to just sit back and relax and do the same thing that we've been doing for the past 10 years. What we really want to do is something new with machine learning, and so that's what I'll be talking about. So if you look at this schematic for TDE score, this sort of encodes basically what we were doing before machine learning in terms of how to discover TDE. So these were the features that we were using, not with a classifier, but just with our astronomer brains. But you could definitely say that this is open to a lot of potential biases. So, you know, maybe TDEs do happen in AGN and we're very biased against finding them. Maybe we should consider removing some of these properties. And the nice thing about machine learning algorithm is you can actually just switch off pieces. So you can take the same data set, you just remove 2/3 of the variables, you retrain it, and then you see what you find with specifically just a subset. And so what we did is we retrained this classifier to look only at the properties of the light curve. So every single ZTF transient that is detected is now analyzed by this algorithm and given a score that basically says, does this light curve look like a TDE or not? Does it match these properties that I was telling you about? And I want to talk to you about the recent source that we found. So this is TDE 2025 ABCR. This is the light curve, again, ZTF and Swift data. And you can see that it displays all of the great properties that I was telling you that all TDEs should exhibit. So it rises over a period of 30 days, fades over a period of 40 days or so. The offset between the various bands is roughly constant, and it's extremely blue. It's very bright in the UV. And just to quantify that a bit further, if you compare this source, so this is the source in orange, to the overall population of ZTF TDEs from the first few years of the survey, what you find is that it has an incredibly average rise time, an incredibly average fade time, an incredibly average temperature, an incredibly average cooling rate. So in all respects, this is an extremely boring source. Why am I interested in it? Well, just to convince you very further that it is indeed a TDE, obviously, we checked to be sure. So we took a bunch of additional follow-up data. These are kind of all of the hallmarks of a TDE. So all of the things you can do to be really, really certain. So we looked, has a very typical TDE-like light curve, but there's also no historical AGN activity at the position. We took a bunch of spectra, clearly blue continua, as you expect. We have broad hydrogen and helium, again, as you expect for a TDE. We have the UV emission, that it's luminous and it's not cooling. And we also have luminous variable soft X-ray emission. And again, this is the classic TDE signature. So some of these properties might be shared with another class, but there's no population that has all of these properties together except for TDEs, which we know about. The reason that I'm talking to you about this rather boring TDE is that it has one very interesting property, which, as you can see in this image very clearly, it is not in the center of a galaxy like I told you we expect TDEs to be in. So what instead we have is, so the source here is in blue, and then right next to it we have a spectrum of the host galaxy. These two things are exactly the same redshift, and there is an offset of 10 kiloparsecs from the center of the galaxy to where the TDE happened. And yeah, if you look in a legacy survey imaging, there's really nothing at the position of this TDE in archival data. Now, what's really nice about TDEs is that we're getting better and better at extracting physics from them. So now if you look at a TDE light curve, you can get a pretty good estimate of the mass of the underlying supermassive black hole. And for this TDE that we have, we're pretty sure it is around 10 to the 6 solar masses. For this host galaxy, obviously you can do all kinds of analysis with the spectrum. We have a spectrum and we find that the host galaxy has a 10 to the 9 solar mass black hole at its center. So what I'm showing you in this image are two different black holes. And again, I just want to really reiterate the point. What I'm telling you is that we have a TDE that came from something that probably looked quite a lot like Sagittarius A star. Sagittarius A star is obviously the black hole at the center of the Milky Way. We expect that this black hole probably once had a Milky Way around it, but when we look at it now, this Milky Way galaxy has entirely vanished, and there is really absolutely nothing at the position of the supermassive black hole. And not just a Milky Way, there's not even a sort of something comparable to the Magellanic Clouds. That's how deep our limits on prior mission is. So how can you have an off-nuclear TDE? How could it be that this sort of thing would happen? And the idea is actually not that complicated. So if you imagine that every galaxy has a supermassive black hole at the center, what would happen if two galaxies merged? Well, then obviously you're adding a second supermassive black hole. And what we actually think is that over time, if you have a big galaxy and a small galaxy, a minor merger, over time, the smaller galaxy gets tidally stripped as it moves inwards, and so it will become fainter and fainter and fainter. And perhaps at some point, it loses almost all of the material in the galaxy, and then you're only left with the supermassive black hole and maybe a nuclear star cluster. Eventually, we think that these systems migrate inwards and form a close binary. And of course, this is of very great interest for LISA and other multi-messenger observatories. But what we also think can happen is if you have a binary, these can be stable over quite long periods of time. And if you imagine now you have a big galaxy, you've had a merger a long time ago, and now you have a new merger, so you introduce a third supermassive black hole to the system, then in that case, we expect that there are these dynamical three-body interactions that occur, and basically the lighter of these three supermassive black holes will be ejected out at velocity and migrate outwards from the center of the galaxy again. So looking at our source, there were several plausible scenarios for where the supermassive black hole should come from, but we have some key observable constraints. So the supermassive black hole for the TDE is 10 to the 6. The supermassive black hole for the galaxy is 10 to the 9. Clearly, these are very, very different scales. So that means you couldn't have had a major merger. And you also couldn't have had some other scenario involving the central supermassive black hole somehow migrating outwards. Instead, what we think is likely is that either a minor merger or this dynamical induction scenario could explain the observations that we see. And I'm running out of time, but let me just take a step back and think about what this really means, because there is apparently this population of wandering supermassive black holes. Now, I think I always have this mental image in my head that a galaxy, it's, you've got your disk and your bulge, and you've got one big supermassive black hole at the center. But simulations tell us that this is actually not right at all. And instead, if you look at more massive galaxies, you could have dozens or even hundreds of supermassive black holes within a single galaxy. And this population is extremely hard to measure because most of these supermassive black holes are not actively emitting light because they might not be actively accreting, and so they're pretty much invisible. And TDEs are one of the only ways that we can kind of pierce the veil and see that these wandering supermassive black holes exist, how common they are, where they are hiding. I just want to remind you that there are actually now 2 low offset optical TDEs. So we heard already about Yuhan Yao's wonderful AT 2024 TVD source, which was detected very close to the center of the galaxy, but clearly offset. Just last month, there was also a confirmation that another known ZTF TDE which was spectroscopically confirmed, was detected in the radio. And what you see is that you have the radio position of the TDE and the radio position at the center of the galaxy. And those two things are clearly offset because this is another off-nuclear TDE. And so I think a really fundamental question is, how common are off-nuclear TDEs? And we have blind classification programs that are looking for just all kinds of transients. So the transient that I've just been talking about, 2025 ABCR, we can say it's not 1 in a million necessarily, but at least of all of the supernova, 10,000 that were classified by ZTF, there's really nothing like it. So it's at least 1 in 10,000. But then actually, if we look at the population of very bright TDEs, the ones where we have the best chance of actually measuring an offset, there's only 24 of those, and we now know that 2 of them are offset. So this is already at least 10% of all TDEs that are very nearby are not in the center of galaxies. And this is a lower limit, of course, because it's not always easy to measure an offset. So it could be that actually many of the TDEs we already know about were off nuclear the entire time, and we just didn't know about it. So this is something we're very interested in continuing to study, and an archival analysis is ongoing between myself and Yuhan Yao, so we expect to have results later this year. So let me just sum up and remind everyone that the landscape for transient astronomy is incredible. Sorry, this next Thursday is wrong, but like last month, Rubin has started. How far we can actually see TDEs. You see ZTF is right up here in the corner. We can see to 19.5-ish. That gives you a very tiny parameter space, but obviously with Rubin, you can go all the way down to 23.5. So we expect to be detecting TDEs out to redshift of 1 or beyond. Roman is kind of comically deep, out to redshift 4 or beyond. And the other thing is that for this particular source, again, we had a 10 kiloparsec offset. Even at redshift of 1, Rubin would be able to measure that this was an offset TDE. So this suddenly opens up the possibility that every object like this, up to redshift of 1, could be detected and discovered with Rubin. So yeah, let me just sum up. TDEs are indeed a unique probe of quiescent supermassive black hole demographics. We discover most TDEs with machine learning already. We recently begun a systematic search for off-nuclear TDEs. It took us only 3 months to find this source, which makes me very optimistic that we can find more. The wandering supermassive black holes can have several origins, and TDEs are really the only way to study them, I think, or at least one of the only direct ways. We might find a lot more with ZTF. I am really confident that we definitely will find a lot more with Rubin. And yeah, so when it comes to supermassive black holes, not all who wander are lost. So thank you very much. I'll take the questions.
Thank you. Questions?
Really nice stuff. So I'm curious, in this minor merger picture, the fact that you don't see a host, means that that black hole has been there for some time, and presumably you've had many TDEs. Do you have any thoughts on other like environmental ways to look for wandering black holes, basically like some effect of the TDE on the nearby environment, not just the TDE itself?
So I think even aside from TDEs, like people do propose that you can identify wandering supermassive black holes just by looking like gas dynamics and kinematics in galaxies. That's one of the main ways people have looked for it historically. I think it's just always so much harder to, like this is just a very smoking gun way of doing it, but I think there definitely are indirect probes that should be possible as well.
Can I go first?
Where do I look?
Me. I had a question about, you said, so maybe this this like wandering supermassive black hole has some nuclear star cluster. I mean, it has to have something to have the TDE. Would it ever be possible to observe something like this? Or do you have an idea of what redshift we could try and observe some like star cluster for these things out to? Maybe Rubin or Roman is a good case for this.
Yeah, no, that's a great question. So there have been other off-nuclear TDEs discovered in the X-ray where the nuclear star cluster was detected, like but they are sort of sitting not very far below our prior archival limits from legacy survey.
Okay.
The problem is that the TDE is there, and so if we look, the TDE will still be there. If we wait a few years with JWST, for example, I think it would be very, very feasible. And as you say, the stars, in some sense, they must be there. So I would really be excited to go and directly detect them. I think we definitely can do it.
Yeah, I forgot for a second how long the disk can last in these things. So yeah, okay, thanks.
So I know it's a small sample size, but is there any evidence for like systematic differences with the rest of the nuclear population?
So there is one key difference in that. So all of the off nuclear TDEs so far, they're in very massive galaxies, which makes sense. I mean, that agrees with our expectations from simulations. The bigger galaxies should have more wandering supermassive black holes. The other thing is that, so there's this scaling relation between the this one. Okay, so basically this is the peak luminosity and the black hole mass. We think that more massive black hole means more luminous TDE. The ones, in particular, this one that we found is very underluminous. And that, again, makes sense. So this is a possible way of actually identifying TDEs that might really be off nuclear, is just looking at ones that aren't roughly nuclear but seem to be very underluminous. Maybe it's because they're coming from a lighter secondary supermassive black hole rather than the primary one whose mass we already know about.
This question.
Yes, I want to ask the host of this nuclear TDEs, or are the host Green Valley galaxy like normal TDEs?
Yeah, I think there's not really a key unusual property about the host. Like, they're just more massive, but otherwise they're pretty normal. Yeah, there's nothing exceptional. I mean, like I said, like the two that we found archivally, we didn't even know that they were off nuclear initially. They just looked very normal to us. So yeah, nothing special there.